Okay, today we're moving on from bolted fasteners and connections and all that stuff. And we're moving into chapter 9, which is introduction to well, actually, the whole chapter is, let's get the whole name, welding, bonding, and the design of permanent joints. So fasteners were meant to at least be capable of being taken apart. Maybe not the rivets. You can take them apart by drilling them out and everything. But now we're looking at things that are meant to not come apart. Not very easily, anyway. So we're going to start with welded. Other things in here are, adhesives and things like that we'll get to later. But we're going to do welded joints today. There's lots of different types of welding. You've got friction stir welding, where you just spin the pieces together and they generate enough friction heat that welds them together. You've got oxy-acetylene welding, where you're going to get the torch and the flame and everything, and you're melting material directly with that. You got TIG and MIG welding and all those wire feed type weldings, where there's some inert gas that surrounds the weld site. And you're usually adding some filler, some wire feed, so wire that's getting added to that joint. And then there's stick welding or arc welding, or whatever you want to call it, the ones that use an electrode. So there's a stick of filler material. Sometimes it has flux on the outside to help the welding process, kind of like that inert gas does in the MIG and TIG welding. But that's the one that we're mainly going to focus on, although what we're doing doesn't actually have a lot to do with the way things get welding, other than we may specify an electrode. In general, when you're welding something, you want the thing, if you are adding a filler, which most welding processes do add some kind of filler material like the electrode, you want that added material to be stronger than the base material that you are welding together. And so you do normally specify, or it is, in our case, maybe the electrode material is given to us and we're trying to figure out some other thing. But that's what we're going to do. We're going to look at the introduction to this. So we'll spend a couple of lectures on welded joints. First one will be similar to how we started with fasteners, where you just have axial loads, and then we'll move into stuff with eccentric loads, where there's another primary and secondary shear you have to worry about. So we'll look at some welding symbols. There are different symbols when you want to maybe call out a weld on a machine drawing or something that you've created. There are welding symbols. Maybe you want to read one of them. We already talked a little bit about types of welding, but there are different types of welds themselves, and so they all have different symbols, different names. And then we'll look at actually, we won't look at a joint in torsion. We won't look at that. Stresses in, let's just say, welded joints, because we won't do torsion today. This is a little bit blurry. Let's see if we can make it a little bigger in some parts here. Maybe not. This is a chart in your book. Let's see if I can find it. Yeah, this is Shigley 10th edition, chapter 9 is where welding is, in the 10th edition anyway. Maybe we can look at this in our book and it might be clearer. Let's see. So this is figure 9.1. Let's see if we can look at it over here. Well, it's going to be difficult. It's at the bottom of the page, so it's going to be difficult. So here it is over here, figure 9.1. It's not much clearer. It is a dense figure, a lot of details on here. But the general thing you're looking at is there's an arrow and there's a line. And those are the pointing out where the weld is going to occur. And so things underneath this line are going to happen where the arrow is pointing, and things above this line are going to happen on the other side of where this arrow is pointing. So sometimes, instead of maybe drawing two different arrows to both sides of a joint, you draw one arrow to it and say what's going to happen on both sides of it. Sometimes you're only working on one side, and sometimes the other side. So the arrow is going to point to a feature on a drawing, and then beneath this line is going to have some symbols and numbers that will indicate what's going to happen on that side, and then above it will be what's going to happen on the other side of that feature. Things that might show up on this include the shape of the weld. So let's go back over here and look at this. There might be symbols similar to these that are going to show, is it a fillet weld? So does it have a triangle? That's going to be our most common one. That's the one I think that we will exclusively deal with in this book chapter, or fillet welds. But there are other kinds of welds, as you can see here. Your book goes through and maybe draws out a couple of these different ones. But fillet, the one that's a triangle, is going to be the one that we're primarily going to be interested in. So that shape, here's a example of the arrow side. Underneath the line is showing that there's a fillet, meaning that on the side the arrow is pointing to, so this little corner right here, this joint, there's going to be a fillet weld. We'll talk about this number in a minute. And then there's a feature on the top side. So the top of this line is the other side. So the other side of this joint where the arrow is pointing. So over here, realized I was pointing that you couldn't see where I was pointing. So here's the feature we're talking about. So the arrow is pointing to this side. Beneath the line is what's happening on the arrow side. Above the line is what's happening on the other side of the joint. They're both triangles, so they're both fillets, and you can kind of see this dark gray area here is the fillet weld. You know, it's showing the welded new material that you've added. The pinkish color is the parent material that you're adding to. Now, just because these are different materials, they're steel usually, and doesn't mean that there's no interaction between the parent, the pink, and the filler, the gray. You actually do want some amount of interaction between those two. You want to create a little zone around this joint where you've mixed these materials. Now, I will say that your book has one process that is super simple to use. It's basically a chart that we'll look at later, and it does not consider mixing of the electrode material and the parent material when it goes through and uses that chart. So it will not be the most conservative calculations you could make, but it is very simple to use. Actually, the other equations are not much more complicated, but this is really simple to use. Let me look at the chart real quick. It's this chart right here, table 9.6. That's really blurry on your screen, so we'll have to look at it in the book. But it looks like this, and it is very simple process to use that chart. And we will use it. We'll show you how to use it, but I'm going to show another way that is more conservative to assume that you've added heat here. You're literally melting two pieces together and then adding a third filler material, and you have to assume that if it's molten in there, that you have mixed some of that electrode and parent material together, and it's made the electrode material a little bit weaker than what you started out with. The other thing that happens is these parent material, they may have had some treatment, like they might have been cold drawn, or they might have been heat treated somehow, and then you went and dumped a lot of heat, enough to melt metal into that area, and they may not have, and you probably don't want to assume they have that same original strength that they might have gained from being heat treated or gained from being cold drawn. So what you do is a conservative estimate. Now again, the welding and designing welds and actually applying welds is a whole career by itself. So we're going to be just looking at the very top layer of this thing, and if you were actually doing any of this work, specifying welds, or if you were doing the welding yourself, then there is a whole other level of detail that you need to know. So we're making super conservative approximations, estimates, assumptions when we do this. So like I was saying, there's going to be a zone of affected material around here. Maybe if I draw a little circle where this might be. Now, there's no like exactly where this zone is going to exist, but you know, somewhere in there around that fillet. Let's make it like that, but let's make it where you can see through it. There we go. Oh, well, I just undid it. Sorry. All right. So some material around there that has been affected by all that heat that you put into it. And so what might have happened if it originally had properties of being heat treated or cold drawn, which are going to be stronger properties than the original just hot rolled material, is that this little area somewhere around here and on the other side too is probably going to be a little bit weaker. And so you might want to consider using the hot rolled material properties versus the cold drawn or whatever heat treated area that the rest of this, you know, whatever's out away from that heat might have had originally before you started welding. So do keep that in mind also. So what we're going to do is we're going to work on these weld problems a couple of different ways. We're going to do one where you just use the chart in the book, super simple. And then we're going to do another where maybe you do make a conservative estimate that, well, these properties in here probably changed a little bit on the parent material, and we're going to look at that too. Here's some other, it's kind of small over there, but let's make it a little bigger. So right here, here's another weld call out. This one looks a little different. First, it does have fillets, so there's two triangles. They're offset though. They're not lined up like they were over here. So this is a kind of like your welding and then skip a space, weld, skip a space, weld, skip a space. And that's what this set of numbers here is saying. This is how long are you welding, and then this is how far are you spacing between them. Now this one does not specify the weld size, where this 5 over here, it did specify the weld size. So what this 5 refers to is, well, I didn't say this, but on fillet welds, you generally assume that this is a 45-degree right triangle. So that 5 would be the leg. So either this leg or that leg would be 5. You'd have to assume that's millimeters. You wouldn't think it's 5 inches. That'd be a massive weld. So 5 millimeters of this distance or that distance. Both of them should be the same, ideally. And so over here, they're not actually specifying the size of the weld, but the spacing. The 60 is how long do you weld, and then the 200 is the spacing between them, or well, between their centers anyway. Let's see. Oh, let's see. Here's another one. This one has a different idea on it. So it has the 5, so it's a 5 millimeter leg. This one's welding like a cylinder. This is a top view, this is a side view. A cylinder, there's our circle we can get rid of, onto a square plate or some kind of plate. And so it's got a fillet weld. So that's kind of this gray area around here. You can kind of see it over here too. It has 5 millimeter leg, so 5 and 5. And this circle, that's a new feature on our diagram. What this means is weld all the way around. So notice it's the arrows pointing up here. This is one thing that always confused me when I started looking at these things at the beginning. Whenever I started looking at these, is the arrow side, even if the arrow is pointing up, is beneath this line. So beneath the line is the arrow side. No matter where the arrow itself is pointing up or down or whatever direction it's pointing, under the line is what's happening on the arrow side. Above the line is what's happening on the other side of the arrow. So we have nothing on the other side of the arrow, which would be inside this hole. So it would be inside here if we were going to have something above this line. But we have a 5 millimeter fillet weld on the side of the arrow, so where the arrow is pointing. And then this circle means go all the way around. So go all the way around that perimeter. Whatever shape it is, doesn't have to be a circle that you're welding around. It could be a square or rectangle or whatever. You just go all the way around the perimeter. If we did have information above the line, then that would put stuff inside here, like I said earlier. All right, let's see what else. There are a couple other features on here, like this colored in dot means that it's a field weld, means that you get the machine or whatever it is you're welding in place out in the field and you weld it there. So maybe you have to weld this to some existing fixture that's already out somewhere, and so you have to do it outside. And then there's all these other features. We're mainly going to only worry with the shape. So is it a fillet or some other shape? The size of the weld, so the leg size in either millimeters or fractions of inches. And then maybe the patterning, you know, the length of the weld and the pitch, so this L and P over here. Those are, and maybe the circle going all the way around. Might need that. Here are some different weld symbols for different types of weld. So these are all varieties of butt welds where you put two pieces of material butted up against one another and you weld in between there. So this is the traditional one where you didn't do anything. You just cut the pieces off, put them next to each other, and then weld it across that seam. But in order to strengthen the weld, maybe you've done a couple of different treatments to the end. So over here, you've ground it down to have a bevel in there, an angle. Maybe you've done that to both sides. Maybe you did that only one piece. So all of these are different ways to get basically more electrode material in there so that you have a better idea that you have fully welded everything. Now, you do have to assume that whoever is doing the actual welding is professional welder. And there are many techniques on how to go back afterwards and determine that these welds were sufficiently made. So there's all kinds of inspection techniques that happen afterwards that ensure the welding was done properly. All right, so here let's do one thing before we get to that. All right. So let's make sure I've gone over everything that I wanted to talk about. We talked about mixing of the parent material and the weld. We did say that the electrode, assuming that you're using an electrode, so that's the filler material, is stronger than the parent material. You normally get some amount of reinforcement. So like over here, you can kind of see where there's a little hump above, there's some extra filler material in there, so you get a little bit of extra material. Now you don't want a whole bunch of extra material. A lot of times these get ground down. That might be because maybe you just want it to look nicer. Maybe it needs to interface with another part, and if there's a lump where that weld is, it won't interface properly. Or maybe you want to eliminate any stress concentrations that might occur when you have this nice flat area and then suddenly there's a hump on top of it that creates a little corner down there. So maybe you want to get rid of that. But there generally is some extra material that provides reinforcement. On these fillet welds, I made one. So I don't have a way to actually weld over here. So I had to make one out of different materials. So let's get this out of the way. So here's my parent material, that's wood, and here's my fillet weld in here, just this clay stuff. And so this would be a fillet weld. Let's see if we can kind of look at it from the end. And it would have, now mine didn't come out with this perfect, let's adjust it a little bit to make it look more like what I want it to look like. More like that. So it didn't come out with, nice, exactly the same size on both ones. You do want this to be a right triangle. Let's focus better. There we go. All right, nice little right triangle in there. So my parent material, and you want this side and this side to be equal. Now what we're assuming that's going to happen when these welds fail, if they fail, we have to analyze them to see how much force we can expect them to hold, or if they're big enough to hold a certain amount of force that we're applying. We don't expect this to happen. We don't expect the parent material to just come off of the weld, either side. we expect these parent material and weld to become one material. You know, they're melted together. That's the part of the mixing thing that we were talking about earlier. What we are going to check is that if the throat of the weld fails. So we're going to call the throat of the weld this little thing right in here. So let me show what we expect, or at least what we're going to guard against, is failure like this. Something like this. So that throat right there, that surface is going to fail. So it's a 40 or 45 degree, well, no, I guess, yeah, 45 degree angle from that back corner, and it's going to shear on that throat. That's what we're going to measure, or not measure, we're going to calculate, analyze. But we don't expect the weld to just let go like that. If this happened, then whoever welded it did a poor and incorrect job of getting enough heat in there. And you can kind of see that if you have a weld that is bubbling up, you know, it's just looks like it's sitting on top, it's lots of little blobs, then it probably didn't get a lot of mixing with the parent material and the weld material. It's just kind of sitting on the surface, and then you might have something like this where the weld stays in place and whatever you welded to it just pops off. That is not a proper welding job, and we are not analyzing that, because that means that whoever welded it just didn't weld it right. We're going to assume that whoever welds this welded this properly, and that for it to fail, that it has to fail by shearing that throat in there. So the two parent pieces don't really, you know, maybe they mix a little bit. You might have, if they mixed a lot, then you've probably added too much heat, because you've melted, you know, way down in here and way down in here, and they've mixed together. That might happen a little, but you don't expect that to, that's not generally what you're trying to do. There are other techniques like friction welding where that's what you're trying to do, is mix the two parent materials together by, you know, rubbing them together fast enough to where they actually bond to one another. But what we're talking about is we're adding a material. There will be some mixing between this weld and this parent, and the weld and this parent, and hold it all together. And then we're going to analyze what happens if it shears on this throat. That's called the throat of the weld. Other features of the weld, just so we have names. So let's look at a drawing versus that, because it's hard to deal with. So this will be one parent material. There's another parent material, and then we've got our weld in here. So this piece, actually there's two of them. Lost all my pins. We're going to call this and this, those are legs. And so those are the ones that get specified, their size gets specified on the call out, you know, the one that had 5 millimeters. That's that distance and that distance. The throat is going to be this guy. And we chose that one because, first of all, materials like this are weaker in shear, and this is going to be a shear plane, and it's the smallest area that we could create. Now, I've drawn a line, but remember, it's actually a whole area here. So it's the smallest one we could create. You know, this, if we chose this, that's a larger area than this one. This is the smallest one. So that's the throat. And that's the surface we're going to analyze. You also have the toe over here. And I suppose you have the heel over here. We don't use that for anything. But anyway, those are the main features that we're going to talk about. Throat, toe, leg. Leg is also weld size. We might call it that. So those are the things that we're going to talk about. All right. So now let's go back over here. What this equation, these are some assumptions that we're going to make. Some of them we've already talked about. So first, there's not an analytical approach that accurately predicts what you might measure in your experience, or if you did a bunch of experiments or whatever. And so there's not just a equation that perfectly matches up. So for us, at our level of welding understanding, without being a professional weld engineer, then we're going to use pretty simple and very conservative models when we go specifying welds. So what that model is going to look like is any of these external loads that are going to cause failure, they're carried entirely by shear forces on that throat. So we're only looking at shear forces. So we're going to look at shear strengths, and we're going to look at the throat of the weld failing. This equation is basically the shear stress on that throat surface of the weld. So F is the external force, 0.707 is because we have a 45-degree angle. H is, well, we didn't talk about H. H is how long the weld is. So not the leg size, but how long is it? Did you weld for 6 inches or whatever? L over here is the leg size. So that's basically the area of the throat. And then here is the force. Force over area is a stress, but this particular one's a shear stress, so we have a tau. This is the same equation, they just moved the 707 up to the numerator for some reason. And we're not looking at normal stresses on the throat, only shear stresses. That gives us a, yes, it could fail some other way, but the shear stress, if we design for shear stress failure, that should be the most conservative thing we could come up with. And there is this maximum shear stress model that says that what we're doing is going to be a factor of safety of 1.17 greater than that maximum shear stress model. So here's an example. All right, so we have a weldment that has this orange piece, parent material, welded to this gray piece, parent material. We are using a 3mm. Now you do have to make sure of a couple of things here. You couldn't specify some size here that is so large that the parent material can't actually support that. Like you couldn't specify a 1-inch weld and then have a 1/2-inch plate, because how are you going to get the 1-inch weld on something that's only 1/2 inch tall? So you do have to have some limitations here. So we're using 3. Let's get this back to the size it was. We've got 50 by 50 millimeters. There's 100 millimeters hanging out over here. We don't really need that information. We have the axial force over here trying to basically pull this orange piece off that direction. And we don't want that to happen. We've welded it in place with a 3mm fillet weld all the way around. So this circle means that we went all the way around. Now this one's a little interesting on how it goes all the way around, because out here it's obvious. It goes here and here, down here, and then this orange plate is on top of, or in front of, the way we're looking at it, the gray plate. So there's nothing to weld to on top of the orange plate, so the rest of this weld that goes all the way around actually occurs on the back side of the orange plate. So on top of gray here, and then underneath the orange here, to go all the way around. We have this specification that the shear stress in the weld is not allowed to exceed 140 megapascals. So that's basically the strength of the weld. First, let's do this one using the charts. Now, to use the charts, you actually have to have an electrode material. Let's look at this chart in our book. This chart. It's kind of hard to see on my slide here, so we're going to find this table 9.6. And we'll show you how it works. If I can find the thing. Let's see. Well, should be. Oh, there it is. Table 9.6, page 483. All right, so it's one of these that turns sideways on us. Maybe I can. Oop, that didn't help you. Can't turn it that way. All right. So what's on this chart is, well, there's several pieces of information. Over here, you have the electrode material, so it's going to 60, and this little asterisk, usually there's a, maybe it says 60XX, or there's two numbers out there that specify the electrode further. The 60 talks about the strength of the thing in general. So 60, 70, 80, then you got 90, 100, 110, 120. So the 60 refers to all of this column, and then 70 all this column. Let's just say we have a 60XX electrode. Now our problem statement actually just gave us a allowable stress that we're not going to exceed. This works differently. So if we had a now another thing, our chart example problem with the orange and gray pieces, that's in metric. This chart, and it's the only one we have in our book, is in US units. So you do have to do some converting between them to be able to solve one and the other. So 60 electrode, 60XX electrode, it has allowable shear stress here of 18, and you have to read to see what the units are, and they're in KSI. So it says KSI right there. So 18 KSI. That's useful. We could use that information, but if you keep going down, they have this line: allowable unit force on fillet weld, kips per linear inch. And they give us this formula. It says 12.73 times H. So let me write that down. So we'll say the electrode is a 60XX, and again, these X's might have actual numbers in some settings. For us, we're not interested in what this part is doing. We're only interested in the 60 series electrode. So it said that, and it gave this F equals 12.73 times H, and that unit is kip per linear inch. Okay. So we have that already solved out. So basically they've taken the strength of the material, the electrode material. Now this is the chart that does not assume there's mixing in the weld material and the parent material. So this is less conservative than what we'll do later. So we have H, and 12.73 is the number from the chart. Now they actually even make it simpler than that in some cases. So if you keep going down, the leg size, I think I just said it again backwards again, where I said H was the throat. H is the leg size. So they have some common leg sizes. Now again, it's only in fractions of inches. So if you, in our case, we have metric, which is not going to be in this chart. There are other charts like this that would have metric values already built into them. But let's just say we have a 3 millimeter leg size. So, that's going to be in the, I don't know, 1/8 inch range or so. So maybe if you had one of these, they just tell you, they basically solve this equation. Basically, they put in H into the 12.73 equation, and then they just give you the allowable unit force for already solved leg sizes, so weld sizes. And you take that number. Now, all of these numbers are 12.73 times H, and all of these are, you need to multiply by how much weld you have. So in our case, we can just use this one. Now, we do have to worry with the fact that we have a metric, H for us, bring that back, H for us is 3 millimeters, and our equation here is going to give us kips per linear inch. So let's just convert over. I think your book, in case you don't remember, I think your book does have conversion factors. Back on page, it's really in the back, 1014, I think. Yeah, so back here, there's a lot of different conversion factors to get from one unit system to the other. I don't know if they even have well, they have yards to meters, so you could do it that way. I assume they just expect you to know inches to millimeters or centimeters, something like that, because I don't see it in here. So hopefully you know that 1 inch equals 2.54 centimeters. Now we have millimeters, so 1 inch equals 25.4 millimeters. So we do need to be able to convert between those. All right. So if we have a 3 millimeter, let's convert that over to inches because our equation up here is expecting inches. So 25.4 millimeters is 1 inch. Let's calculate that to see how many inches of weld we have. So 3 divided by 25.4 is 0.118. So we were close if you did the 1/8, because that'd be 0.125, so kind of close anyway. Inches. All right, so what I do is this is H. That's the size of a leg on the weld that we want to put all the way around this block, this orange block over here. 12.73 times H, so, and that'll be kips per linear inch. Well, the units that when we generate them are going to come out as kips per linear inch. So maybe they don't tell you what the units on 12.73 are. So we'll just do it this way. But the units are going to come out as kips per linear inch. So let's multiply this number times 12.73 and 1.50, we'll say. And that will be thousands of pounds per linear inch. So that is not the actual force that this welded joint can hold. What this is for every inch of weld that we put on here, it'll hold 1,500 pounds. So we have to go back and figure out how much weld do we have. So it doesn't matter, since we're doing everything in shear. Remember, shear doesn't care if you're shearing in one direction or the other direction. It's all shear. So we got to figure out how much shear we have, how much shear area. And except not area for this equation. This equation wants just inches of weld. We've already taken into account the area size when we multiplied times H. That 12.73 has factors built into it that are taken into account the area based on the weld size. So we have 50 millimeters, another 50 millimeters, another 50 millimeters, and the 50 millimeters behind the orange plate, so underneath it. So we have a total of 200 millimeters of weld. So we have 200 millimeters of weld. Again, we got to convert that over since we're in linear inches over here. So times 25.4 millimeters in 1 inch, and this will tell us how many inches of weld we have. So it's just 200 divided by 25.4, 7.87 linear inches. So we have 7.87 linear inches of weld. Each linear inch can hold 1,500 pounds, and just multiply those together and we'll have just kips. So F here, the maximum force that we can put on here according to the chart is, so this, we'll put this as max, equals our 1.50 kips per linear inch times we have 7.87 linear inches. That's a times, not equals. And our total value is times 1.5, 11.8 kips. So it says that using the chart that we could put 11.8 kips on here before our welds would fail. Now, this chart is, again, it's not considering the mixing of the base material or anything. It's just it's a chart put out by the, I believe, AISC is probably, I can see it down there. That's the American Institute of Steel Construction, and so they generate this chart, and it's based mainly on the electrode material. It is considering only shear failure in the electrode material, but it's not considering mixing or anything like that. A more conservative approach would be to use this version of the equation. So let's try that. Let's move that out of the way and see if we can figure out what to do with this sort of setup. Okay, so our equation, tau equals F. So again, F is that maximum force that we can apply. Well, in this case, because we have a tau max given from our problem statement said, let's go back to it. The shear stress in the weld is not allowed to exceed 140 megapascals. Okay, so we have tau max already given to us. Now, I will say that this 140 and the 60 series electrode, they're not meant to match one another. So it's totally possible that we get a higher strength this way, even though it's the more conservative method, because this 140 is not necessarily the same as a 60 series electrode. This is just a number we picked. I just wanted to show you how this one would work, and that it's not significantly more complicated. Things you might do to generate this number. So if it's not just given as it is in our problem statement here, where you just have a specification given, maybe you have a material property. So we'll take a little aside, and let's say that you just had a material property that you're dealing with. So let's say that you have an electrode material which is stronger than your parent material. So that's one of our design considerations that we just normally have, that whatever you're going to weld this up with, the electrode is stronger than the parent material. We're going to assume that they mix together, and that weakens the parent material and brings some of that parent material into the weld and so forth. And so there's some zone of mixing that we don't really know what the properties are. So what we're going to do is we're going to assume that those properties are the weaker material, even though they might not be, and it might only be a small area that's weakness. So let's say that you had a 1015 cold drawn material, steel. Let's say that, and I think that might be where this number comes from. I don't remember now, but let's just pretend that we do have this 1015 cold drawn. So you have to go back to find, this is the parent material. The electrode material is stronger than that. So we have to go way back into the appendix of our book. This is going to be table A20, I think. So way back here. Oh, not that far back. 22. Okay, so here's table A20. So let's see if we can point out some of these things. So there's 1015 cold drawn. So we have, these are not the numbers that the 140 lines up with. So we have a tensile strength over here. We have a yield strength, and we have a couple of different numbers here. So cold drawn are going to be stronger than the hot rolled, but what we're going to assume is that the welding process heated up at least a small region around the weld that doesn't have the cold drawn properties anymore. So you're going to use the hot rolled properties, which are weaker. So you have a tensile strength of 340 megapascals and a yield strength of 190. Now you do have to remember that we are dealing with shear, so you do have to convert those numbers over to a shear strength. In fact, let's also look at, well, let's write those numbers down. So 1040 SUT is 340 megapascals, and yield strength is 190 megapascals. Okay. Now, there's another chart in our book over here. You might can read that one, table 9.4. It does look a little blurry though. Let's see if we can find it in the book. I have it right here. So table 9.4. So right here on page 482. And what it does is it goes in and gives you permissible stress based on the type of weld you have, and there's a little footnote down here. Well, first of all, it says that over here it's using distortion energy theory, so that's the 0.577 to get the shear strength. But down here, this little footnote, shear stress on the base material should not exceed 0.4 times the yield strength of the base material. So that's one factor. And then you have a bunch of different types of butt welds where you've put two pieces next to one another and welded in that seam. And then you do have the fillet weld down here. So the shear on the fillet weld. So the permissible stress in that case is 0.3 times SUT. So let's see what that would be. SUT times 0.3. Calculator. (102 megapascals). And then the other one, the footnote said that the shear stress on the base material should not exceed 0.4 times the SY, the yield strength of the base material. (76 megapascals). So you can see where there are some different considerations that you want to think about. Now this one, it doesn't explicitly say this, but you assume that what they're talking about here, since this is the shear on the base material, you kind of assume that they are talking about what I said you don't expect to happen, where the base material shears off from the weld. That's probably what they're actually referring to with that 0.4. But you might as well treat that one the same way that we've been treating the others, as the shear stress in the throat of the weld. In basically what you would be assuming there is that you went in and completely mixed the welding and base material and created some alloy, I guess, that has a much weaker strength. And why you might want to do that is that it does create a smaller area. Going back over here, the area between the parent material and the weld here shearing off is larger than the throat area shearing off. So again, we're just doing things as conservatively as possible. So this is another way, if you have a parent material specified. So what we did is we specified the parent material, but then we converted it, when these properties, we converted it to the hot rolled version. So they're a little bit weaker. The yield strength is way weaker than the cold drawn version. And then use table 9.4 to calculate some limiting strengths there, which would be significantly different than otherwise. Now this number was just given to us in the problem statement. So someone else went in, did something like this to figure out, hey, the maximum that we can allow is 140 megapascals. So however you get to that tau max, you use it. whether it's just given in the problem statement or you go look up. Now, obviously, if you are doing this for actual weld specification, there's not a problem statement. You know, you do have to go find the material properties and decide for yourself what is the best shear strength to use. So we've got our 140 F max over, again, this is the area, the shear area on that throat of the weld is basically what this is giving us. We had a 3 millimeter, so going way back to our problem statement, we had a 3 millimeter weld size, and then we had this one still does assume that we are just adding up the amount of weld, total amount of weld, so 50 plus 50 plus 50 plus a 50 behind there, so it is still 200 total. And then we just solve this equation. Now we do have some, you know, millimeters over here and megapascals over here that we have to deal with, but then we can just solve for F max. So let's see, 140 times 10 to the 6 pascals. Let's just convert everything to the base units. So 3 millimeters, that'll be 0.003 meters. And then this will be 0.2 meters. And let's calculate that. So 0.707 times 0.003 times 0.2 times 140 10 to the 6 megapascals. And that gives us F max as 59,388 newtons, or 59.4 kilonewtons. Now, we mixed and matched our unit systems here. The first time we did with the chart, we had kips, so pounds. Over here, when we solved it again, we kept it in newtons. Probably would be better to be able to compare those. And those conversions, I'm pretty sure, are in that table on page 1014. Let's see. In case you forget that one, that's not one you use as much as inches to millimeters and such. So let's see. If there's a force, pound force to newtons, 4.45. So you could, if you ever are unsure how to convert most things other than inches to centimeters or whatever, that one you just need to remember. Maybe you write it in down here. That is on page 1014 for your conversion factors to get from one to the other. Okay, so that gives us a general idea of how we're going to deal with pretty straightforward weld scenario. You know, we didn't have any pattern. So let's say that there was a pattern, you know, weld, skip, weld. The procedure that we used isn't any different. It's still the total amount of linear welding. It doesn't matter if it's horizontal or vertical or at some angle. It's just you add up all the weld length, and that is what is going to go into either, you know, this equation with L, or the chart, the numbers from the chart over here. This one, again, you have to know the electrode material. This one, we're kind of assuming that we've mixed everything together and the parent's weaker than the electrode, and we're going to use that weaker material property. And so this is much more conservative than using the chart on table 9.6 in your book, just because of the way they're set up. Okay, next time what we're going to do is we will do the same type of thing where we have something welded to something else, except we're going to push down. So maybe something like this. You know, now we've got this thing wanting to shear, you know, shear directly, and then also rotate. And so there's a primary and a secondary shear. This is going to look a lot like the bolt with an eccentric load, bolt pattern with the eccentric load. It's going to look very similar to that. And there are some special charts in your book that help us out with this, finding the centroid and things like that of weld groups. Okay, I think we are good for today. We will pick back up on this on Wednesday, and if I did go back and say that the L was the weld leg, maybe I was thinking, I can't remember if I said that or not, but H is the size of the weld, and it refers to how the length of the leg of the weld. So the 5 millimeters is basically the base of that right triangle. I just can't remember what I said. I'll have to go back and look and see. Anyway, H is the weld size, not how long it is or something like that. It's the size of the weld. Okay, we will see you next time.